Okay, the second part of Chapter 6 is on analysis of variance, or ANOVA. Unfortunately, analysis of variance is a bit of a misnomer because the analysis you're doing is really about means. But people still call it analysis of variance, and I'll tell you why in a moment. Really what we're doing here is an extension of Chapter 5, which was on 2-sample testing for means, to 3 or more. We're going to call it M samples. So our model for this analysis, this is going to be a little bit complicated at first blush because we're going to try to write M samples compactly and generically. So we're going to use double indexing. So the ith sample from the jth population is notated as Yij, and it has a Gaussian distribution with a mean mu j. So each group j has its own mean and a common or pooled variance sigma squared. So they all have the same variance. This is really important for some of the math to work out. It's not as important if you're doing simulation, and there's a couple homework problems on that one. But we're going to stick to the pooled analysis for this video. All right, so I've got I equals 1 up to each sample can have its own nj number of samples, and then j indexes over the groups. And if we were in Chapter 5, m would be 2, and we'd be doing the pooled analysis from Chapter 5. But here in Chapter 6, we're going to do m samples generically, and so j will go from 1 up to m. Okay, so the hypotheses, or the want to know, the null hypothesis is that all of these means, all m of them, are the same, versus the alternative that at least one of them is different than another one. This is kind of a compact way to write that. So the null hypothesis is that all of the populations have the same mean, and the alternative is that at least 2 of them differ from one another. Okay, so let's look at some data where we might want to do such an analysis. So I'm going to go back to the ice cream. I'm going to sort of continue where we left off, and I'm going to introduce a third data set, which will be measurements of weight of fat-free ice cream. So now we have genuine ice cream stored in Y, and sorbet stored in X, and fat-free stored in W. And I'm going to put all of those into one big list of Y values. This is convenient in R because we can automate over the entries of the list. And the entries in this case are cream, sorbet, and fat-free. Okay, so that's our data. So here's an example of how we can automate with lists. So extracting the n's and the m's from this data. So what I can do to get each n, or each nj, I like to call the variable nj, so that matches up with some of the math. I can do sapply, which is a function that will apply anything you want over a list. So I'm going to give it ylist, and I'm going to tell it I want the length. Okay, oops, I got to spell length correctly. So nj is the lengths of each of the entries in the list. And then the total number of groups in the list is just the length of this nj vector, and the total length of all of them is the sum of the nj vectors. So I should have m groups, 3, that's correct, and my total number of samples, 26, is the sum of 9, 7, and 10. So now what I want to know is do all scoops have the same mean, right? That's my null hypothesis? Well, my null hypothesis is that all the scoops have the same mean. All right, so going back over to the whiteboard here, under the null hypothesis, we know how to calculate the grand mean, so I can just calculate y bar, which is the sum over everything. So I need a double sum to sum over everything, and then divide by how many there are. And if I want to, I can call that mu hat, but going forward, I'm just going to use y bar. And I can get a grand estimate of the variance too in the same way. Again, I'm going to need a double sum. And I'm going to do the usual yij minus y bar squared. Okay, so in R, let's do that. So I can get y bar as the mean of something, and what I'm going to do is use the unlist command to take away, let's see what that looks like. So unlist of ylist is just going to strip away and give me a vector that just has everything all in one place, all in one vector. So y bar is the mean of the unlist of y. And I can do the same thing for the variance. It's the variance of unlist of y, or ylist, excuse me. Okay, so those are my estimates of those parameters. So under the null hypothesis, that is the mean that everybody shares, or that's my estimate of the mean that everybody shares, and my estimate of the variance that everyone shares. Okay, so let's get a little more space here. Unrestricted, so that is under the alternative hypothesis. Oops. I could get separate, need separate estimates of parameters. So for example, I can get the mean for the jth group, which actually I'm going to notate as y bar dot j. So the jth group, with the dot is kind of representing all I equals 1 to nj samples being involved in this estimate. So I'm going to divide by nj, and then I'm going to sum up all of the yij's for that group. And I can do that separately for each group. Okay, so in R I can use the sapply function to help me do that. So my y bar j's are going to be sapply of y list and mean. Okay, so this is going to give me 3, or m y bar j, 3 or m estimates of the mean. And same thing for the variance. I can get a pooled estimate. Remember, they all share one variance, but in this alternative hypothesis, they have different means. So I can take, well, maybe it's better to do things in a different order now that I'm thinking about it. So I can get separate estimates of the variance, nj minus 1, I equals 1 to nj. So this is just kind of chapter 3 stuff. Right, those are my separate estimates, but under the model that I've set up, I really have just one, and so I can get the one estimate, or a pooled one, by averaging all of these estimates. So I'm going to have sj squared, but first I'm going to get rid of the denominator, and then I'm going to divide by a grand denominator, with an adjustment for degrees of freedom. Okay, so this is m is the number of y bar j estimates. So it represents my degrees of freedom. So I'm averaging, and this is over j, right? I just don't have enough space for it. So here's how I do that in R. So I'm going to get an S2j, which is S-apply of the variance command. So that gets me the separate variances, and then I'm going to put them together by summing up nj minus 1 times S2j, and then I'm going to redenominator it, divided by n minus m. Okay, so there's my pooled estimate of the variance. Okay, so I think I'm all caught up in R with the calculations that we're doing in the notes. Now here's some of the magic of ANOVA. I don't think you're going to find it magical, but let me show it to you anyway. Okay, so developing a good statistic for testing involves relating the null and alternative hypotheses and their mean-based quantities What do I mean by that? I mean all of these things, right? These are all estimates of parameters. I've got a lot of them. I've got m mu hats, and I've got m sj squared, so that's 2m. And I've got S2 pool, that's 2m plus 1. And then I've also got from over here, I've got the null hypothesis one, so 2 of them from there. So I've got 2 times m plus 3, I guess, if I counted correctly. That's a lot of statistics. Those are all statistics, but we want to have one statistic in order to make our hypothesis test manageable. So we relate all of these via their residual sum of squares. Sometimes called SS. And if you look closely at what I'm about to show you, it really is kind of trying to make this complicated number of parameters boil down to a two-sample variance test from part A of chapter 6. So I told you analysis of variance is really about means, and it is really about means, but the way that variance comes in is that all these means and their variances get boiled down into one F statistic that looks a lot like a two-sample variance F statistic like we talked about in the part A video. Okay, so here is something that you're going to show on your homework. There's a homework question in chapter 6 on this. So if I take the grand sum of all of the deviations of the data from their grand mean squared, so this is j equals 1 up to m and I equals 1 up to nj, this can be written as, or decomposed is maybe a better word, so into the following. Up to nj. So here we've got the differences in the individual means from the grand mean. And then we've got a plus here. I've got the same pair of sums. And then we've got the differences between the individual observations and their group-specific means. This thing is known as SST. It's the total sum of squares. The sum of squares from all of the data around their grand mean. This is called SSR. R stands for regression, but that's, again, a bit of a misnomer. We haven't talked about what regression is yet. We will in Chapter 7, but this is just how people write things down. It's not super important what the R means. And then this one here is the sum of squared errors. So these are the errors of the individual group mean estimates with the individual values in each group. Okay, so let me show you how to calculate that in R. Calculating the sum of squares. So SSE is sum, sum of nj minus 1. We'll talk about this in just a second. Times s squared j. Okay, so let's look at that. We've already got the individual sums of squares. You can see that the individual sums of squares are involved, but we have to multiply by nj minus 1, which is the denominator up at the top. Let's see, I'll make sure to point that out here, right? We've got this denominator here that we've got to get rid of in order to work with just the part that involves the residual sum of squares. So that is SSE, and then SSR is going to be NJ, or sum. It's a sum of NJ times Y bar J minus Y bar squared. Okay, so look at how this right here is part of the formula, right? So that's there, but we don't want the part of these y bar j's that has the denominator nj, so we're multiplying that away to cancel it. And then finally, the total sum of squares, I could get that with a big sum, but it's easier to just say that that is the sum of SSR and SSE, just like it says in the formula, right? So back here we have SST equals SSR plus SSE. Okay, so we did the calculation in R, and we've developed the identity for sums of squares. Now here's something that's obvious, I think, once I say it. Any part over the whole is a proportion. So what I mean by that is, if I take SSR over SST, that will be, I'm going to write this over here, that will be a proportion. So it'll be less than 1. It'll also be positive. Oops, I'm getting ahead of myself. It'll be positive because these are sums of squares. So squares are always positives, and sums of positive things are positive, and ratios of sums of positive things are positive. So it's between 0 and 1. It's a proportion. People call this R squared. And the reason why it's called R squared is kind of like a story for later. It's a chapter 13 story. But we'll talk a little bit more about R squared when we get to chapter 7 on regression, and that's how the R is involved in SSR. Now, since it's a proportion, you can also calculate it as 1 minus the other one. If you want to. Just like saying that if the probability of heads is p, the probability of tails is 1 minus p. Okay, so I can calculate this in R. So R squared is SSR over SST. So now I've boiled everything down into a single number. Remember, I had 2m plus 3, or however many of them, into one number, one grand statistic. And that statistic is a ratio of sums of squares, just like the two-sample f-test is. In fact, you can calculate an F statistic, and we're going to come back to this in just a moment. I want to do some simulation before I do the math part, but I want to write this statistic down, which is called F. F is SSR over SSE, not SST, but SSE, and that gets normalized by the number of degrees of freedom involved in those calculations, so that they'll have chi-squared distributions. These are called mean sums of squares, so MSR over MSE. Okay, so I just want to write that down because I'm about to go over to R and do some simulation, and what I want to show you when we're doing the simulation is that there's really not much difference between R squared and F because they involve the same quantities. As you can see, both of them involve SSR and SST and SSE and SST because those are related to one another through this formula. It's just a slightly different use of those quantities. Okay, so as usual, I want to do the test, do an ANOVA via simulation. So what does that involve? That involves generating samples from Gaussian populations and calculating their means and their variances and their grand means and their grand variances, just like we did up here for the data, but doing it for virtual samples from Gaussian distributions. So here, let me first show you how to get virtual samples for M populations. Okay, again, I can use the sapply or lapply commands. It's actually best to do lapply for getting long vectors. So if I do lapply and I tell it I want nj samples from R norm using a mean of y bar and a standard deviation of the square root of S2, that will give me virtual samples in these different categories of the right length, right? I told it that I want nj, which is a vector of length m, or 3, telling me that I want 9 from ice cream, and 1, 2, 3, 4, 5, 6, 7 of sorbet, and 10 fat-free. So that gets me some y's, and then I can go grab my code from up here. I think I can grab all of it, right? If I just grab all this stuff and stick it down here, but then be very careful to change the names of things. So these are my y's that I just sampled, and these are my y bar, I'm going to call this y bar j's, and I don't need to print them to the screen. And these are my S2j's, as long as I'm careful to, actually I don't need this quantity in any of the calculations. Oh no, I do. I don't need these quantities in any of the calculations. I think I need this one. I need the y bar j's. So there, I give this the y's, and I need this one, S2j's, ys. Okay, and then I can get the y bar. The y bar says the following sum of y bar nj times y bar j's over sum of nj. That would just be n. I guess I could have used the code that was up there before, but I'm following my notes here. And I don't need an estimate of the pool variance for any of the calculations that I'm doing. And then I can follow this formula, SSES. So this is going to be S2JS, and then SSR S. This is going to be Y bar JS minus Y bars. And then SST I don't really need. Oh, I do need it to calculate R squared. SSTS is SSRS plus SSES. So now let's kind of, so my R squareds are going to be these guys, SSES and SSTS. And I suppose I didn't go back up here and calculate this F statistic either. So MSR is SSR over M minus 1, and MSE is SSE over N minus M, and then the F statistic is MSR over MSE. So I can follow that same formula down here. Oops, SSR. Okay, by the way, this R squared is called the coefficient of determination. Not a really good word, but I thought I'd say it out loud, and this is our F statistic. Now let's just make sure this code runs. We already ran this one. See if we generate, have any typos. Doesn't look like it. And this I gotta call capital F. MSC's, did I not run that one? That was the problem. Okay, so all that code runs. Now I can put it all in a for loop. So I'm going to do for I in 1 to n. I've already got n defined from earlier. It was 100,000. And then I can indent this properly so it fits in the for loop. All we've got to do for this virtualization is follow the calculations that we did on the data, but do them on the virtual data that we generated under the null hypothesis using estimates of y bar and sigma squared. Now I need to make some space for the statistics that I'm saving. Okay, so now I've got that space and I can save each one. And I think now I can run that whole for loop. And this is kind of a big calculation, but still you can see it only takes a few seconds to do. Okay, so now let's do a visual. The usual histogram of the statistics. Let's start with R squareds. Okay, and you can't see that until I do this, and now I think you can see it. So there's my histogram of R squared values, or I can do a histogram of F's. Oh, I'm seeing a mistake. I'm like wondering why this is backwards. I did my R squared calculation wrong. Let's go back up to where I did it. I said R squared is SSR over SST, which is correct, but somehow when I got down here, I wrote SST. So that should be SSR. Let me rerun the simulation and redo the histogram. I was like, why does that look funny to me? It's exactly the opposite of what it was supposed to look like. So there's the histogram of R squareds, and the histogram of F's, you can see looks very similar. The F's are not bounded between 0 and 1. the same way the r-squareds are. R-squareds have got to be between 0 and 1. F's have a longer tail, but you can see the distribution has a very similar shape. So how do I do testing, or how to calculate a p-value? Well, you do the usual thing. You're going to do mean of the r-squareds bigger than r squared, right? Actually, the better thing to do would be to do AB line v equals r squared so you can see it. And so the observed r squared is now on the plot. You can see the observed r squared is rare under the distribution of r squareds that we simulated under the null hypothesis. And the same thing for the f's. You can see that it's rare. This is one of those cases where there's no two-tailed test. The test is not two-tailed. Under both of them, what you care is how far away the line is from the distribution out in its tail. You only care. And the reason for that is that these are all positive quantities under the null hypothesis. So smaller means closer to the null hypothesis, bigger means farther from the null hypothesis. So you only need to, oops, I accidentally reran the entire file, but that doesn't take very long. There we go. There's the p-value, which is really tiny. So this is going to be an easy reject of the null hypothesis. And we can do the same thing via the f's. And maybe it wouldn't surprise you that you get exactly the same value. So when it comes to simulation, you can use r squared. That's simpler. You'll get the same answer. But the reason for the f version of it is because the math works out a little better. So going back over to the whiteboard, you can show that under the null hypothesis, this f statistic has what's called an f distribution that we talked about earlier with parameters m minus 1 and n minus m. And this is because the numerator and denominator of that f statistic are each chi-squareds of different sorts. I put chi-squareds. I'm not going to be specific about it. If you want to look, you can check it out in the book. So what that means is I can calculate a p-value with the pf function with this f statistic at m minus 1 degrees of freedom and n minus m degrees of freedom, and lower tail equals false, and I get more or less the same answer. So I guess you could quibble that this is 0.3 and that's 0.3. So I'm pretty accurate after rounding to the 100th place. So my simulation could be more accurate with a bigger capital N, or we can use the fancy math here about F distributions. That wraps up Chapter 6.